Okay, so my picture will stay up all the time, right? So I can do like this and people can see it.
Yes.
Okay. But it's somehow time delayed with the hands. It doesn't work so well. I can hear a bell going off all the time. Is that every time somebody joins?
Yeah.
Yes.
All right.
I'm not sure. I'll look into how I can stop that.
Well, it's good to know. If people suddenly start leaving, then I know I've gone wrong.
Sean, any chance you know how to turn that off?
I think it's in a setting when you create the meeting. I don't think it's, yeah, I don't think you can disable it at this point. I think we're stuck with it.
Okay.
So, hi, Joran. Thanks for doing this lecture. I'm really excited to hear it.
Yeah, well, it's a little bit tricky for me because I'm a theoretical nuclear physicist and not a nuclear engineer, and I don't know the audience, their background, and so on. So it's a little difficult. So
Yeah, it's a pretty broad audience. So we've got some undergraduate students, first year graduate students, even several national lab scientists have signed up for the course. So it's like the whole range.
So I don't know their background. I don't know what they have learned. And Stefano told me I should try to keep it fairly basic and simple and so on. So
yeah, I think if you keep it at a high level, and then people can ask questions and we can elaborate.
People usually never complain to hear something they understand.
That's right. Makes people feel good. Okay, so Mike was able to turn off the dinging.
I can't see how many we are either. On
Currently, we're at 60 or 74.
Okay. Yeah.
So people are starting to come now.
Yeah.
And I think I saw that Ramona also joined.
Yeah, yeah.
Oh, Ramona.
She can ask all the tough questions.
I'm on to see how things go because when I'm nearly the last one,
We'll have all the bugs worked out by then, Ramona. Don't worry.
No, but it gives me some idea of what people know also.
So I can hear you guys in Michigan much better than I can hear Ramona in the next room.
I'm on these fancy Apple wireless earbuds.
Yeah.
"91 people.
So now it's time, but you give 5 minutes. Is that what you wrote me, or how does it work?
Yeah, we started around 3:05. I think yeah, 3:05. It looks like we're almost there in terms of participants. We had about 1:30.
Yeah.
But yeah, we'll just give some time for everybody to come in.
Yeah.
Hello. If you can, to the person just asked in the chat, can we get an audio check? If you cannot hear us, well, please let us know.
But if I couldn't hear you, how could I respond?
That's right.
It's just like asking, is everybody here?
Audio is good.
There we go.
Raise your hand if you're absent.
I was going to type in the chat that we were just speaking, so if they couldn't
Uh-huh.
hear us, then.
Aha, so now there's progress on my side, only momentarily. But there was a bar. I moved it in the other display and it disappeared again, but then it came and now it disappeared again. So I thought it was there to stay now, but it isn't. Huh. Hmm. Ah, I see. Okay, when I put my cursor on the green bar that says you're sharing, then I get a black bar where I can mute and stop the video, see that we are 106 participants and so on and so forth. I cannot chat. It doesn't say anything about that, I think.
Between participants and the share screen, it doesn't say chat.
No, it doesn't.
That's not a problem. We can do that.
I think you might see chat if there's a view options button at the top of your screen.
Yeah, there was something that said more, and when I click that, there's a long list, and at the very top, which I missed, it says chat, actually.
And also we have a suggestion from the audience. Try pressing Alt-H. I hope that doesn't destroy the computer.
What?
It will be a good move, Rachel. Very good move.
What?
Alt. There's no Alt on Mac. I think it's Option A.
That's right.
Option H.
I wouldn't, yeah.
Okay, so now that I can see the chat, what is it I do with it? It says chat 5. What should I now do with it?
So people can post their questions in the chat, so you can periodically check it and address any questions that might come up as the lecture goes on.
But I can also, I'll
yeah,
do that.
Stefano's going to monitor it for you. Yeah, you don't need to.
Let Stefano handle this.
Yeah.
Yeah. So
I don't want to be multitasking.
well, I think it's 3:04. So it's not 3:05 yet. Okay.
Good build up, Stefano.
I was hoping that by the time I, prepared everything, it would switch, but I think it was like just during 3:04. So. Okay, now it's officially 3:05. So it looks like we have most people attending, 111 people. So thank you very much, everybody, for coming back for this week. And so today's presentation is going to be on nuclear fission, and we have a collaborator and a nuclear scientist from Lawrence Berkeley National Lab, Jorgen Randrup, and who has worked in fission and in nuclear physics for many decades. And among his accomplishments is being one of the co-developers of a fusion event generators called Freya, which we're going to talk more about in the last weeks of this school, as well as also introducing the work to the Brownian shape model of nuclear shape dynamics, which has proven to be a powerful tool for mass yield predictions. And maybe we're going to hear more about that during the presentation. So just a comment, there is a lot of people here. So if you have any questions, I suggest keeping them until the end, but if you have very pressing questions, please post them in the chat. I'm going to be moderating the questions, and I'm going to report them to Jorgen if I think they are very important and need to be addressed immediately. And with that said, please, Jorgen, you can start the presentation.
Yeah, thank you very much. Thank you very much for this invitation, which I could accept without the usual logistic overhead. But I regret we can't all be in the same room. It is nice to see people when you speak, and I'm also a little overwhelmed by so many participants. I'm used to a smaller group where it's much easier to have questions and answers as we go along. So I hope we can work it out. If you have some very pressing questions that can help to clarify instantly, then you should ask them. But if it's things you want to discuss and hear more about, then you should better wait until the end. So as Stefano said, I'm a theoretical physicist in Berkeley, and you can see that from the illustration. And you can also see that from my background here, which is taken from, it is if you sit here, here's the lab, here's the Golden Gate, San Francisco is the Golden Gate Bridge, and if you are over there on the hill over there on the north end of the Golden Gate Bridge and look this way, then you have my background view. So you should come out and see for yourself someday. Now this is an introduction to nuclear physics, and I am not so clear on what you already know. You ought to know something since you're nuclear engineers. So let me just start from the basics. Let's see, how do I now do that? I should go up here. Here we go. So here's a nuclear chart that I picked off the web from an Isolde illustration, and it shows that if you have, for example, an actinide nucleus, it can split into two, and typically you get a heavy fragment and you get a light fragment in two distinct groups, which was a big puzzle. So this is nuclear fission, and it turns out to be a very kind of rich process. If you study nuclear fission, you come around to many, many areas of nuclear physics. And we cannot cover them all today. Let me, this doesn't quite work so well. So let me do like this. Okay, so there are different stages of nuclear physics, kind of time-wise. So first, you have a target nucleus like what you saw in the illustration. You have uranium-235, for example. You shoot something on this target nucleus. Typically a neutron, but it can be photon, a deuteron, whatever. And then you have to wait or see until it's over, until you have reached equilibrium, because you can have pre-equilibrium emission, you can have some evaporation before you finally wind up with a compound nucleus in equilibrium, and that is the one that will fission. So this is not fission per se, but it is of course a precursor to fission, and therefore part of the fission physics. Then comes, so I'm talking here today about induced nuclear fission. You can also have spontaneous nuclear fission. Then you can skip this preparation stage. You have already the nucleus. Well, it's much more difficult to treat because you have to go under the barrier and tunnel and so on, and I cannot say anything about that today. So now comes the interesting thing, in my opinion, that this nucleus somehow splits in two. And this is, so the shape evolution, I call it. So you start with one nucleus and you wind up with two. They're not quite nuclei yet. This is called scission. This is where the two parts lose contact. And you have sort of two clumps that will become primary fragments. They will they split, they are repelled by the Coulomb force, so they are accelerated, they get some motion, 200 MeV of kinetic energy or something. They can rotate and they are excited. This is why they are red. And the strange shapes they had just when they split, they relax and they acquire their equilibrium shapes. So in that sense here now, fission is over. But the fission physics is in a way not over. And over here on the right side, I show that these primary fragments, there's a lot more happening to them because they are highly excited, rotate, so they will typically emit 1 or 2 neutrons, maybe more, depending on, to cool down by neutron evaporation, and then they will cool further down to the ground state by photon radiation, and this all happens fairly promptly, and you get then the prompt products. What they are, as you may remember from the first view graph, you're lying on the neutron-rich side of the stability line. They are not stable, so the beta decay processes will come in, and you get then emission of electrons, antineutrinos, and wind up in another excited fragment that then can emit neutrons and photons and so on, and this keeps going essentially forever, but at a longer and longer time scale until you finally get cumulative yields. So this is a kind of an overview of the different stages, and I will just talk about this part here, the shape dynamics, which is for me the most interesting. It's theoretically the most challenging. Conceptually, it's a kind of puzzling. How is it possible that a nucleus suddenly splits in two, and it can be very difficult to formulate real quantum theories for that. So this is what I'm going to talk about. Now, first, historical notes. There were fission data, puzzling fission data in the late 30s. You know, in those days, you could shoot neutrons on uranium, and then you had to analyze very laboriously, chemically, what came out. And it never occurred to people that you could get fission. So they were very puzzled about what they saw. And it was not until finally Otto Hahn, who was a very careful chemist, he proved that this is really barium that comes out. So he got that result sort of just at the end of 1938. His collaborator, Lisa Meitner here, she had to flee to Stockholm to not get sent to camp. So she was up in Stockholm when she received the news, and she invited her nephew, Otto Frisch, who was a postdoc at the Bohr Institute in Copenhagen, to come up over Christmas. And they then talked about this and decided that what is happening is really fission, and she was finally rewarded with an element named after her. Otto Hahn got a Nobel Prize. And here is first a little bit of a physics before we go on, because it is to me a little bit strange that it was such a shock that fission could happen, because people knew everything there was to know in order to realize that this was quite a plausible process. Because nuclei have essentially two forces. One is the nuclear force, which is cohesive. It is like some glue sitting on the surface of the nucleons. It is short range. It is an attraction, and this is what holds the nuclei together. But then, since some of them are protons, they have an electric charge. Well, then they repel each other, and you get this tug of war between the attractive and the repulsive. And you have a light nuclei, well, then there are not so many proton pairs in it, so the cohesion wins, and you get a nucleus that hangs together very well. But if you go to heavy nuclei, then you have more protons and therefore many more proton pairs. It goes as the square of the proton number. So the cohesive force is being overwhelmed, and you can get a disruption. And this is why you can have fission and why you should expect fission. So now Meitner and Frisch then, they said, well, the nucleus is sort of like a liquid drop. This is a picture people had already had for a while. uniformly charged liquid drop. They thought all nuclei were spheres, little drops would be. And then what Lisa Meitner said is, well, but if somehow you can bring this nucleus into large amplitudes, sort of vibrations, then it can maybe become so big that the cohesive forces no longer can hold it apart and it will split. So this was her idea. And Otto Frisch went back down to Copenhagen and told this to Niels Bohr. And he said, what fools we have been. We ought to have seen that before. And as most things Niels Bohr said, that is completely correct. They were fools because they could have seen this before, but they didn't. So anyway, something like this happens. Now Niels Bohr was just on his way out the door to catch the boat to sail over to America to visit his previous postdoc, John Wheeler. So he thought a lot about it on the ship, and I'll get back to that in a moment. Here, let me just go into a little bit more detail about this deformation energy of a uniformly charged liquid drop. It is a fight between the surface tension and the Coulomb repulsion. And to be more quantitative, imagine you have a sequence of shapes, for example, from the sphere, and then elongating more and more, starting to become more and more binary, finally getting two fragments. So something like what you could experience in fission. Then the surface energy is proportional to the surface area. So that goes up when you deform the sphere. So the surface energy goes up. On the other hand, the Coulomb energy, the further you can get the protons apart from one another, the less the energy. So that goes down. So it's a balance between the two. And the total energy is the sum of the two. Now, if you calculate for a spheroid, for example, the surface area, you get the surface energy as a function of the deformation parameter. And you get a result like this. It's quadratic, of course, so it goes up in some way. And you can do the similar thing for the Coulomb energy, which goes down. You'll notice it's essentially similar. It's a factor 1 here instead of a factor 2. So now which one wins depends on how much Coulomb energy you have on the sphere. As I mentioned before, you don't have all that much for light nuclei, so the surface energy wins and you don't get any fission in light nuclei. But for heavy nuclei, you get a tremendous Coulomb force. So the Coulomb force becomes stronger and stronger, and it will anyway ultimately win because there's really no limit, so it could go down a lot. Whereas there's a limit to how much new surface you can create by just cutting one fragment into two. So the blue one will go up and it will go down. So there will be a barrier, or there will be a saddle point generally, if you look at shapes in more dimensions. So this is then what came out of Niels Bohr's visit with John Wheeler. It's quite incredible. In 3 months, they wrote a long, long paper on fission where they discussed many, many things. And here is a figure from their paper. And they drew, they had this kind of picture in mind, but they also realized that it's not a one-dimensional thing in shape. You can have many different shapes. So here they draw in 2 dimensions, elongation and something else, and draw a contour plot of the potential. So the minimum here then around. So the minimum lies here. This is where the nucleus usually sits. And then the idea is the neutron comes in and somehow sets this shape in motion. They were not very clear on how. But if the shape is set in motion, it will move around like a ball in a bowl, and finally it can find its way over the saddle and then roll down the hill and split. So this was their picture. And they added an important insight. They said, if it really is like that, then it can take quite a long time for the nucleus or for the shape to find its way. So it runs around a lot and it becomes more or less a matter of chance to find the right way. So you don't really need to calculate the whole thing if you want to calculate how probable it is for fission. You just need to know You can use statistical arguments. That's indicated over here. How many states do you have at the top of the barrier relative to how many states you have altogether? And if the motion is ergodic, well, you can calculate the fission rate. So this became a very much used transition state method for calculating fission rates. So this was their basic picture. And it turns out this is more or less a very good picture if you just work it out correctly and in detail. And this is what has been done lately, and it turns out it ends up giving a very powerful and rather simple view of fission. So the first and most important thing we need to do then is calculate that potential energy surface as a function of its shape. And I want to talk a little bit about that because I think this is useful for you to know under any circumstances. So the most efficient way to do that is to use the so-called macroscopic microscopic method. I'll tell you what it is, and I'll explain to you why this is a very efficient way to do it. So the basic idea is that when you have some nuclear property, for example, its energy, or in this case, the ground state masses of nuclei, if you plot them as a function of mass, there's some smooth overall trend, but then there's lots of little fluctuations away from the smooth trend because each nucleus has a specific structure that can make it either more or less bound than sort of the smooth average. So here is an example. Here is the masses or mass defect. You subtract the rest masses of the nucleons, and you can see how they are best bound in mid-range, and then they become less and less bound. And then this parabola is obtained if you just had a uniformly charged liquid drop. The so-called liquid drop model was first introduced by von Weizsäcker in the mid-30s. In those days, people thought the nuclei were spheres. Nowadays, you use a finite range liquid drop model that can work for any shape, but you get a similar kind of curve. And if you subtract one from the other, you can better see the point. And that is that there's a lot of structure to the deviations. So you have a smooth average, that is the parabola, but then you have deviations. And you can see there's some system to these deviations. I put in here the numbers where these deviations are largest, and you recognize those as the magic numbers. So there is specific binding in some nuclei due to the intrinsic structure. And the idea is then to calculate the two things separately, the smooth trends with one model, and then these effects here, structure effects with another model. And the reason is that if you look at the numbers, the binding energy of a nucleus is less than 1% of the total mass. So you need a very good model to get the binding energy right. And to calculate then the microscopic effects, they are percent of that. So you need an enormous accuracy if you wanted to calculate this head-on. The microscopic microscope, what is much more economical. You have a simple model with a few parameters you fit to the overall trend, and then it turns out you can calculate these deviations very simply just on the basis of the single particle levels and so on. So this becomes very powerful and very accurate, and also very general because it can work for any nuclear shape. So it's just what we need. So the idea is then, if you want the potential energy for a given nucleus as function of the shape, you calculate the macroscopic energy of such a shape with this finite range liquid drop model or something, and then you calculate the microscopic correction due to a method that was first suggested by Swiatek and then developed into a real powerful mathematical tool by Swiatek back in the 60s. It's a long time ago. So then you can see what you get. The blue curve is the barrier we calculated before for the liquid drop, the surface and the coolant. And then as a result of the structure, you get a final barrier that looks more like you're used to. There's a ground state, there's a first barrier, second minimum, second barrier, and so on as you change the shape. And the finite range liquid drop, there's a volume term which doesn't change, surface, coolant, and lots of other small terms. Now, there is then the microscopic term. And it has basically two parts. There's something called shell energy and something called pairing energy. Now, they are both related to how the single particle levels are in the nucleus. You could somehow imagine that this macroscopic part, the smooth part, corresponds to a situation where the levels are rather evenly spaced. But they are not, they're never evenly spaced. Sometimes there's a big gap at the Fermi surface, sometimes there's extra density. And you know, if there's a big gap around the Fermi surface, it's hard to excite the nucleus and get extra bounds. That's why you have magic numbers. And opposite if you have extra many levels. So this is what you need to calculate. Before we do that, let me just show you how important it really is with these microscopic corrections. Here is taken from Christoph Düllmann. He showed his interest in the super heavy elements. So he showed the liquid drop barrier for some heavy elements all the way up to element 114, which now is called ferrovium. And they are not so big, and they become small and they finally vanish. But now when you do the microscopic corrections, the structure corrections, you can see you get much more substantial barrier. See, seaborgium lives practically only because of the structure, because of the shell effect. And similarly here as you go up higher. So for the super heavy elements, these microscopic corrections are essential. So now then, single particle levels. Well, it's actually puzzling. Why do you have single particle levels at all in the nucleus? We talked about the nucleus being a liquid drop. And you know, in a normal liquid drop, the individual molecule doesn't get very far before it collides with another molecule. It's not like that in the nucleus. And this is because the nucleus is a so-called Fermi liquid. So it is, the nucleons are fermions. They are subject to Pauli blocking. So if one nucleon wants to collide with another one, there's no final state available, already taken. So it cannot collide with it. So its mean free path becomes long, go all the way across and back again without hitting another nucleon. So it looks for the nucleon just like it is in a field, just a field without any other nucleons. Then you can calculate, and then you can solve the Schrödinger equation. You have a single particle Hamiltonian. Here are the fields, the potential here, you can move in, and then you can get the single particle energies. And you can do this for any shape. Here are shape profiles, and then you do a convolution of some sort, get a diffuse potential, and then you have your Schrödinger equation with the potential, the kinetic energy, and the eigenvalue. You solve for neutrons and protons, and you get some levels. And this can be a big business. Here are plots, so-called Wilson diagrams, because Wilson was the first person to do this sort of thing. So you can see, as a function of deformation, you plot the levels of protons or neutrons. You can see here when you have a sphere, you have these shells, and then there's a big gap onto the next magic number, where you have a whole bunch of orbits and so on. And then as you deform the nucleus, some go up and some go down, and you get a whole jungle. It's a big mess. But then if you go out far enough, every now and then there's some opening here, for example, here and here and here. This means if you have particles, so it just matches to come up here, then you get a good shell effect in that nucleus at that deformation, and so on. So this you can calculate. And now what do you use it for? Well, to get the shell effects, it is very easy. It is based on the simple facts. It is kind of amazing, because when you have a many-body system like the nucleus, and you have the single particle energies, the very naive person might think that if you want the total energy of the nucleus, you just add up all the single particle energies. But of course it's not like that. Then you double count, because the field of the nucleon fields is a part of it, result of a two-body or three-body interaction. So you can't count it like that. But if you ask about the change in the total many-body energy, if you make a small modification, like modify the shape, the change in the total energy is just the sum of the changes from the individual orbitals. So that's the trick. So what you need to do is you calculate the actual density of single particle levels. It's a bunch of delta functions, of course. And then you can smoothen that out with some convolution, and then you have to compare the two. So you do this sum for the actual levels, and you do this sum for the smoothened out level density. So this comes down here. It's like the smooth curve is what you get if you integrate up the smooth level density, and the staircase is what you get if you sum up over the individual levels. And the shell effect is just the difference between the two curves. You can see sometimes it's positive, sometimes it's negative. So that's a simple procedure. That's all I'm going to say about that. And I'm going to say even less about the pairing. What nuclei are subject to pairing, as you probably know. That's why you get odd-even effect in the nuclei. And you have to calculate the pairing correlation energy. And again, you have to calculate it for the actual level density and for what the level density would be if it was smeared out. And the difference in the pairing correlation energy is the pairing effects. I just want to say one thing about the pairing energy in relation to the shell energy. Maybe I can see here. See, the shell energy is negative if you have a deficit of levels around the Fermi surface, because, yeah, as I said, then it's difficult to excite the nucleus and so on, you get extra binding. Now for the pairing, it's just opposite. The pairing correlation energy works best if you have many levels. So the pairing correlation is negative when you have this situation here with many levels. So the two effects are opposite, but the shell effect is larger by a factor of 5 or something. So that's the one that dominates. But it goes differently for different shapes, so you have to do them both. So now we are in business. So the microscopic method for the potential as a function of shape, I talked about how it is. It's a liquid drop plus these corrections, and you get some potential. And I want to show a little more of what looked like what Ness was drawing. So this is a two-dimensional contour plot. It's made on a Nilsson's student Peter Møller made a contour plot for his article, and Nilsson took it to his cousin who had a kiln and made ceramics and said, make something out of this. And she made such a thing here. So you can really see which was used as an ashtray in those days. So you can see you have the ground state minimum here, and then you have the isomeric minimum over here. That corresponds to this one. You have the first barrier here, you go over. And now the horizontal direction is elongation. You get just like here, elongation. The transverse deformation is asymmetry, reflection asymmetry. It's easy to draw out here. So you come out here heavy light or light heavy. So asymmetry. And what you notice is that when you come out in the second barrier region, it is actually easier to go over if you admit some reflection asymmetric shapes. So the nucleus prefers to become asymmetric when it splits. And this was a big puzzle, as you remember from the early days when they discovered fission. They couldn't understand at all why the two fragments were not, out of the same, near center. Why was it asymmetric? Because they didn't know about shell effects in those days. So here you see it really comes out. And let me say one more thing about the shell effects. Why is it in the actinides? And it is because the heavy fragment would like to be close to tint 132, which is a double matching nucleus. So it has extra good binding. And it is so strong, this binding, that effect propagates inwards in the potential energy and lowers the barrier here. Without such a shell effect, the second barrier would also be symmetric and the mountain would go up. But so that's the reason. You have the magic numbers and the shell effects in one of the fragments, and it forces the fission to become asymmetric. And then I could not withstand the temptation to show another picture from 1972, which is myself, Nilsson, and Peter Møller here having lunch at the I House in Berkeley. That was when I first met these gentlemen, a long time ago. But the method still works, remarkably. So how good is it though? So I want to show you how good it is. So this is something that Peter has calculated. Every 10 years, he makes a new calculation to fit to the latest data. So here's the experimental microscopic effects, as I showed before. The data minus the smooth average. And here's the calculated with the method I mentioned. And the difference between the two, you see difference in data and calculation is really remarkably small. It's less than, not less, it's about a half nowadays, a half MeV on average. And you see that it is uniformly good through the entire nuclear chart. So this is I think, a very good method, and it's far, far better than anything you can calculate with more basic methods, because it's very difficult to get 4 extra orders of magnitude right. Therefore, one can also hope that it'll work for any shape, because there's really nothing in the method that says things have to be near the ground state. Any shape, this method works. So therefore, we can calculate the potential energy surface with this method for any shape we want. So that makes it a very powerful method. Now, I will come maybe a little more theoretical. Until now, I have really said nothing about how the nucleons inside the nucleus organize themselves. You know, in an atom, for example, if you have an atom, the electrons inside, they are being drawn into the nucleus, and then you add more electrons and add more electrons, and the whole thing is not uniform at all. And if you go from the light region to the heavy region on the periodic table, the atoms don't really become any bigger, because all the time the innermost electrons are being sucked in by the extra charge, and the last electron just sees the 1 unit of charge because all the other electrons are screening it. So it looks like more or less hydrogen and so on. So all atoms have essentially the same size, which is why you can have so much interesting chemistry. So, but it's not like that in nuclei at all. Nuclei look like this. They have an interior where the matter is pretty much uniform, and then there's a surface region. And as you come up in the region we're interested in, the thickness of the surface region is not so much. It has to do with the range of the nuclear attractive force. So it's like a Fermi or something, and the nucleus is like a 10 Fermis across or more. So this is a relatively thin surface. This is what leptodermis means, having a thin skin. And that makes it easier to describe nuclei. So same bulk density and same width. So this means also when we now discuss fission where we have different shapes, by shape we really mean very specifically we draw something like a surface, and then we know what we mean. We have a surface here, we have uniform nuclear matter inside, and so on. Now, how good is this? This is hard to measure experimentally. This thing here you can measure experimentally with electron scattering, and that supports this, but what about other shapes? So instead of going to experiment, I have gone to my microscopic friends who have developed a microscopic model and tried to do fission with a microscopic model. And the thing about this model is that they have just nucleons and an interaction, and they have no condition about how the nuclei should look, that they should have constant density inside or anything. Nucleons just organize themselves, and you can see they really organize themselves in this way, that it is uniform inside. The yellow ones are the neutrons, and well, it's not that they separate, but this is so you can see the densities. They are uniform, and then you have a surface region. So this is really a good assumption that nuclear systems are leptodermis. So therefore, when you want to make a theory for nuclear fission and nuclear shape evolution, instead of trying to do this microscopic job, which is tremendous, and in fact, so tremendous they can't do very much yet. You can also see they start from the saddle and go down. This is not what we want. We want to start all the way from the ground state, and that doesn't work yet. Anyway, it is much simpler to then just discuss the evolution of the shape. That is just a few parameters to describe the shape, and that's what you can concentrate on. So this becomes also much more economical. So many shape parameterizations have been proposed. The one that's been proven to be the best, it was proposed already a long time ago by Ray Ness, and it has 5 degrees of freedom. So what it says is, okay, it has 3 sections. So the left part, the end here is like an ellipse, rotate around, so a spheroid here, the red one, and a spheroid over here, and then you put some kind of hyperboloid in between that matches smoothly here. So then you get shapes that look like this. And you have all together 5, then, oops, what? So you have 5 degrees of freedom for the shape, the overall elongation, which we need, the neck radius, how thick is it across, it's a very important degree of freedom. That's the one that becomes smaller and smaller as you approach scission. Then you need to let each fragment adjust its shape, and this we know already, because otherwise you cannot take advantage of the shell effects that are developing in the final fragments, as we saw with the tint 132. And finally, the reflection asymmetry, which is important. So this, what Ray Ness said was, this is the minimum number of degrees of freedom you need if you want to have a chance to describe fission. And this has proven true. People have used 3 degrees of freedom or even 2, and they have not been successful. So I think this is becoming more recognized. Now let me just compare with the one you see also. So this section here, from here and down, looks more or less like what they find. So this is a free calculation, no assumption of shapes. And you can see these shapes are shapes that can actually be described within this parameterization. So this is a promising parameterization. And in fact, and this is now Peter Møller again, he used this parameterization to calculate the potential as a function of those 5 shape degrees of freedom. So you set up a Cartesian grid, you know, so and so many, 45 different elongations, 15 different neck radii, and so on, all together more than 5 million different shapes, and then you do this procedure for each one. Then you have a giant table of your potential. And then since you have the computer and the code, you push the button, and you can do it for not just uranium, but for more than 5,000 nuclei, which I have indicated here where they are. So we have a gigantic database, so to speak, of potential energies. So, and they are fairly reliable. So this is a very good resource to have for the fission calculations. Now, as enough about the potential energy. Let me now get on to the actual dynamics. And the important thing there is something that also was pointed out by Niels Bohr even before fission was discovered. This was, he talked about the compound nucleus. He made this little drawing here. Here are the nucleons in the nucleus, sitting there in the potential, whether the neutron comes in. And the question is, how quickly does this system equilibrate? Does it, and what Bohr pointed out is that it equilibrates long before anything else happens. So before another neutron is evaporated or it fissions or anything else, it will equilibrate. So in other words, the memory is lost very quickly, or the memory time is very short. So the key thing is that the internal relaxation in the nucleus is much faster than the typical time scale of the shape evolution. And this means that when you want to make a dynamical theory for the shape evolution, you can save yourself a lot of work, because mainly it is dominated by phase space. Because, you know, when you equilibrate very fast, then you go to whatever phase space tells you to go, consistent with the constraint of the shape. So this is a key feature of nuclear physics. It becomes, another way to say it is that the shape evolution is highly dissipative. So it's like pouring a glass of honey, a jar of honey or something out. It goes very slowly, and there's plenty of time to equilibrate all the time. This now, this means we are really nearly in business to calculate things. But of course, since phase space is important, you need to be able to calculate phase space. And what that means is you need to be able to calculate the nuclear level density, but not the nuclear level density you're used to. You're used to just having a nucleus, which corresponds to sitting here, and then there's a level density. But what we need is for a given shape, not necessarily a round state shape, but any shape, we have to calculate the level density. So so we have here again a sketch of the potential as a function of the shape coordinates as we go from the sphere and out towards scission. And then in any given event, we have a total energy determined by how much energy the neutron brought in. That's the green line. And now when you are at a given shape, for example here, some of the energy is tied up in potential energy and the rest is local excitation energy, the thing that gives rise to a temperature. So the local excitation, local means local in shape space, means for a given shape. You have an excitation energy E star, depends on the shape, it is just the total energy minus the potential energy. This is pretty clear. And now you need to calculate the level density here. And now you can see that here, if you are at the minimum here, you come up, you have quite a lot of excitation. So you have very dense levels up here, many, many levels at this energy. If you are, for example, at the top of the barrier, you have a lot less excitation. So the level spectrum is not as dense, you have a smaller level density here, right? So it is clear the level density depends on which shape you have. It also depends not just on the excitation energy, but it depends on the specific shape. Because as you saw from the Nielsen diagrams, the levels go up and down when the shape changes. And this means there's a lot of structure in the level density that changes from shape to shape. All of this you should capture in your shape-dependent level density if you want an accurate description. The simplest is to ignore the structure effects and just use a Fermi gas level density. Just for illustration, but this has been done a lot, actually mostly done. So the Fermi gas level density is e to the 2 square root of the level density parameter times the excitation energy. And these are now shape dependent, both of them. So you can do that, and then you can, do one more here. Probably. And then you can see, you can go here between the different shapes depending on the, if the shape moves around and it's only dependent on the phase space, then if the shape sits here, it would rather go to here than to here because there are more states here, but it sometimes goes to here. So you have a kind of random walk guided by the shape-dependent level density. So one more thing about level density. So the Fermi gas level density is rather primitive. It is better to take account of the actual structure effects. And this can be done. There are microscopic ways to do that. I don't want to go into that. But you take the same levels that you used for the potential energy. You make quasi-particle excitations, many, many millions of them. You bunch them together and you get the actual level density, and you can take into account the whole thing can rotate. So this way you get the shell effects and the pairing effects included. And also when you go high up in energy, these effects become less significant, as you know, because it all smears out without any parameters. So once you do it, this is a very powerful thing to have. So one way or the other, you calculate a shape-dependent level density. And then I think we are ready to consider how does the nucleus actually go from the compound nucleus to scission. So the nuclear shape evolution is phase space dominated because of the very short memory time. And this means that we can, it's like a random walk I was just alluding to. So here is a little bit more of an illustration. So you sit somewhere in shape space. Here's a shape. You look around, there are many shapes that are similar, a little bit different, and you could go to either one of them. So you ask, what is the level density of these different ones compared to what the level is where I sit? And the principle is If the level density is higher, well, then you go. And if it is lower, well, then you may not go. So you make a random selection based on level densities. And maybe you chose this one. So then you go to here, and then you repeat this procedure again. Maybe you go to here, and you continue like this. And in this way, you have generated one walk through the whole shape space from where you started and down to scission where the nucleus splits. And then you do this thousands of times until you get a good kind of a good diagram, a good histogram of the masses that come out of this. So that is really conceptually simple, also practically simple. Nicholas here, Metropolis here, invented a simple method for doing that. So that's what I just said. If the potential goes down, you take this step. This means this is the same as saying the level density goes up, and vice versa. If it goes up, you go on with the Boltzmann probability. And then you make your random walk on this potential, not on this, but on a potential energy surface. So here is the walker. You start here, you go around and around. But if you have enough energy, you can go over the first barrier sooner or later. You come into the second minimum, run around there for a while, then more likely than not for this nucleus, you go back here again, because this barrier here is lower than the second barrier. So go back and forth, millions of steps, but sooner or later you come over the last barrier, and then it goes pretty much downhill from there until you come out and split. So start at the minimum here in the ground state, and then you wait until the small neck, then it's easy to guess how the nucleus will split, and you can then bin this in the diagram and you get a mass distribution. So this was a kind of simple idea I had a while back, and this was the very first result of this. So you see here plutonium 240 fissioning, uranium 236, and here's a uranium 2. So this is the very first shot, no parameters, no nothing, and remarkable agreements. So I don't want to bother you with that. So a lot of studies have gone into this. I just want to emphasize that we tried. I did this with Peter Miller because he provided these potential energy tables, which were used, of course, indispensable for this. So there was an experiment some years earlier done at GSI where Karl-Heinz Schmidt made no less than 70 nuclei that fissioned in some kind of secondary beam experiment, never mind what, but he gets them. He can put, the whole thing is moving fast, so you can put these into a spectrometer and find out precisely what the charges are. So we try to compare with all these 70. This one in red, we fitted kind of one parameter that had to do with the level, with the energy dependence. And then we compare all the rest of the 70, and I don't want to bother you with it, but you can see overall remarkably good agreement. So this is a useful tool, we believe, and we have put it to good use. I see on my clock we are at 45 minutes, so I will go through quickly just a few applications. Here, this is a calculation with about 1,000 nuclei fissioning, and you can see you get asymmetric fission, symmetric fission, and so on. Then we plot it in a different way, namely just ask, is it symmetric or is it asymmetric? By looking at the yield at symmetry versus the peak yields. And if it's asymmetric, that would be 0. If it's symmetric, that would be 1. So you have a color coding, and you get something like this for these 1,000 nuclei. So the actinides are in the red zone up here, where it's asymmetric. We knew that. Then you go down, and fission becomes symmetric. We also knew that. But what we didn't know is that if you go down and out here, you get an entire region out here where fission is asymmetric. That was not known at the time, and it was a huge surprise that there was more or less simultaneously an experiment by Andreev, Lichio, and others, where they managed to look at fission from Mercury all the way out here, 180, and they found it to be asymmetric. to everybody's huge surprise. And now more experiments have been done to try to verify that there really is such an asymmetric region here. So this has given a lot of things to do for experimentally. So in that sense, it's a very useful method. You can make predictions with it without having to adjust the parameters and without having to use enormous amounts of computer time. So that is quite useful. More recently, we have extended this calculation up to the super heavy region. And you see, for example, we also predict there's an asymmetric region up here in the super heavy region and also somewhat out here to in this region here. About this, so I just want to mention one more thing. In the super heavy region, we predict asymmetric fission here. And let me show just for several regions where the fragments go. If we take the actinides, they're the green ones. The heavy fragment, as I told you, lies to be near 10 and 132. So that's here. And then the light fragment must become heavier and heavier and heavier as you go to a heavier and heavier compound system. Then we look also at the rare earth region where they go and in the neutron rich region. What I want to draw your attention to is what happens in the super heavy region. These are the red diamonds here. And they are so heavy that lead can be a fission fragment. We don't usually think about lead as being a fission fragment. And it plays the role you can see as 10, 132 plays for actinides, lead 208 plays for the super heavies. And even more so, you can see they really like to split asymmetrically because then one of the fragments can be lead 208. And the other one must then be whatever it takes according to the conservation of mass number. So this is a prediction. We don't know yet if it's correct or not, but it's an example of how you can use this simple method to make predictions that you can go then and check experimentally. And hopefully you can learn some physics from that. So I am over time now and I will finish. So this was supposed to be an introductory lecture on nuclear fission. Nuclear fission is an enormous field that touches many, many things. And in your summer school, you have a whole week for gammas and a whole week for this and a whole week for that. So many, many aspects. And I talked just about this relatively little part over here, but it is for me the most interesting because it is the most challenging from the theoretical point of view. How can it be? All the other things are conceptually simpler to imagine that, an excited nucleus can emit gammas is not so strange to imagine. You just have to make a good model for it. So I want to mention one thing here. I wrote in the first slide, I say that this is where one nucleus turns into two. So I wrote from 1 to 2. Here I have written in Latin, ex uno plurus, and this means out of one you get many. And what does it mean? It means that you don't always get this particular final configuration. You can get many other kind of fragments. It's not the same fragments every time. They don't have the same shape every time and so on. So just from one simple state, even if it were spontaneous fission, one ground state, you can get many, many, many different, qualitatively different final states. This is not an easy task to deal with for theorists. I mean, if you solve the Schrödinger equation, you always get the same result. So that's a big challenge. And that is why this random walk is so powerful here, because with a random walk, it is different every time what you get. So this is extremely well suited for this particular kind of process. So the shape does like Brownian motion. It's just a random walk on the potential energy surface. I told you about how to calculate this one with this microscopic method. And I told you about how to calculate shape-dependent level densities. So this is a simple, beautiful picture of nuclear dynamics, I think. But it is more than that. It is also a powerful calculational tool because it is not just conceptually simple, it's also practically simple. And I showed you that it gives quantitatively good results, and we can therefore go ahead, use it to survey and predict and so on. We can get not only the mass yields, we can also generalize to isospin, so you get mass and charge yields. you can, once you have the scission configuration that in a given case, you get like 30,000 different scission configurations. They all look different. Each one then moves apart in a different way. You get a whole distribution of total kinetic energies. So you get that information also, and you get the yields gated on that, and many other things I can't talk about. And finally, just an advertisement, recent results this year, 2 from a group in Lund I work with, where this whole business lastly originated. One is about the excitation energy partition. These two proto-fragments, they are very excited, which is why I make them so red. And they are both, but the excitation energy is not distributed as you might think. Typically, the actinide state doesn't go to the heavy one because it's a magic nucleus. It doesn't have so many states. So it's the light one that gets most energy and therefore emits most neutrons. So if you look at the neutron multiplicity as a function of A, it behaves in a peculiar way. And this you can try to understand. And you can especially take advantage of also looking at the TKE, because the more TKE you have, the cooler fragments are, the fewer neutrons you get. So you can use that. And then finally, but not least, I want to draw attention to this paper by Mumpower. It just came out a few days ago. We have calculated nearly 4,000 different nuclei, the mass yields in fission for our process nucleides. And there's a giant database available to anybody. You just go in and take it. So if anybody wants to do fission network calculations or anything in the R process region, you are welcome to use these mass yields generated as I have described. So that is it. Thank you very much. Sorry I ran over, but this is the end of it.
Thank you very much for the presentation, Dr. Randrup. I think it was very good. And I see some questions coming in already, if you have some time to answer a few.
I must say I'm impressed, because when I started, there were 111 people, and I wanted to see how much it had dropped to. And now the number is 115, I saw.
Yeah, they invited their friends. So the first question that we have is from Avik, and he's asking, how did they predict the liquid drop model, and was it based on some experiments?
Well, yeah, so there have been many, many generations of liquid drop models. And the physical idea is that, roughly speaking, the nucleus behaves like a uniformly charged liquid drop, right? And once you have said that, well, then you know what there has to be. There has to be some term proportional to the volume. There has to be a surface tension, so surface energy, and then there has to be a Coulomb energy, which you can calculate just like a uniformly charged sphere. So this is the original liquid drop model by von Weizsäcker. And I should add one thing, that contrary to normal liquid drops, the nucleus is a two-component system. It has neutrons and protons. And although the interaction, the nuclear interaction between neutrons, it is strongly attractive and so on, it is more attractive between unlike nucleons and like nucleons. When I lecture about this in my daughter's school class, I say it's like people. There's more attraction between unlike than between like people, 3 times as much. And this is why on the nuclear chart, you tend to get equally many neutrons and protons in the nuclei, because that gives a better binding. And it's only as you come up higher, when you then have the protons to make it unfavorable to protons, you tend to get more neutrons than protons then. But what this means is you have to also have a term that's called symmetry energy. So nuclear matter has a binding energy, not just depending on the total density of nucleons, but how different is the neutron density from the proton density. So the volume term has also a symmetry part. So there are kind of 2 terms there. But as far as fission is concerned, they are both volume terms, and nuclei are highly incompressible. So the volume is always the same. So they don't really play a role for the potential energy surface. So anyway, this is the idea, and then you just go out and fit to the data. And then 10 years later, you make another fit because the data has improved and so on. But meanwhile, you may also have thought up some other corrections. There are higher order corrections, and there's this and there's that. And if you want to see the state of the art, you can go to that Mumpower paper I managed, because Matthew said, look, we use the finite range liquid drop model, but it's not really explained in full anywhere. There's a little bit explained in one paper, a little bit in another paper. We want to write the whole thing down, so this you can do there. All the terms are there, all the parameters, and so on. And then basically they are refitted every 10 years or something like this to, and they change slightly. So it is, I don't want to say a phenomenological thing. It is not a basic calculation.
Yeah.
I hope this answers the question enough.
Yeah. Yes, yeah, that end. A second question we have is from Rob Goldstone, who's asking why there are so many closely spaced resonances for high Z elements. And is that because of a liquid drop effect, or is because of some single particle level spacing effects?
Yeah, now you're asking something I actually don't really know anything about. But these resonances are relevant, I think, when you bombard, you shoot the neutron on the nucleus, right? And if you look at the cross section, you see a resonance structure. Right. I suppose is what you're talking about. There's something I don't know anything about, but I have always imagined, understood that it has somewhat to do with the single particle structure. Because if you have orbitals, you have orbitals in the nucleus, whether occupied or not. And these orbitals are probably not occupied, but they are there still as a solution to the Schrödinger equation. And now you come in with your neutron. And if you have the energy just right, so it matches such an orbital, well, that seems to me like favorable, and you get a spike in the cross section. And if you come in where somehow in between, it doesn't really work out so well, then it's not so easy to absorb the neutron, and it just goes through, I suppose. So I think it does, to a high degree, reflect depend on the structure of the nucleus. And I think, and therefore also it will depend very much on the shape. If you could somehow do the same experiment on the same nucleus at a different shape, you would see something very different, I predict. It's a prediction.
So one of the last questions is, who understands the internal structures within the drop, which assume the liquid drop model, with proficiency to predict resonances? So I think the question is, how well can we predict resonances?
Similar. And what I said before is just total speculation on my part. It's something I never worked on or really learned anything about. I do not know what is the most reliable way to calculate those resonances. And I think it's my impression it's a tough job because there are so many of them. They are so close lying, and it means you need a gigantic accuracy of your model if you want to get them right. I'm sorry, I cannot help you with that. I came here to talk about fission, not about resonances.
Then there are some questions more technical about like where the slides will be available. And yes, I believe they will be made available on Google Drive. I have a question that was directed to me, probably, but I can ask you as well, is the semi-empirical mass formula, so the one that we use to predict the masses of the ground state masses. How far are these semi-empirical methods to predict structural and geometrical properties of nuclei?
Yeah, so there was one line on one of the slides I went over very quickly because this was the slide where I showed that Peter Müller had calculated all these data tables, 5 million shapes for 5,000 nuclei, and why? And what he used it for was primarily to calculate ground state properties. So he wants to find out what is the ground state shape of a nucleus. So you have to calculate the potential and find out where the minimum is. You don't need 5,000 or 5 million, whatever shapes for that, but he was also interested in locating the fission barriers, where they are in shape and what their energies is. So then of course you need a much larger domain of shapes. And it's a lot easier to put in a Cartesian grid, even though most of it you never need. So, but anyway, his purpose there was to extract also, you could say, geometric properties, not just the masses and the fission barrier heights, but also the shapes. So the deformations, the quadrupole deformation and octupole deformation and so on, of saddle points and both ground state shapes and isomeric shapes. So And this is why I got into this game, because I was talking a lot to him, and I always thought he has all this information, but it's not really being used, in my opinion, very much. It ought to be possible to use it for some dynamics. And this is, this is how I got sucked into this, started thinking about it.
We have one last question for now. And maybe there is going to be more in a second, but for now it's a basic question, and it's can a probability be assigned to the formation of the daughter products? So I think the question could be phrased as do we only predict the mean masses of the fragments?
No. Oh yeah, no. This is very important that you predict. With this approach, you predict distributions, right? You make a simulation, and this means you make one random walk. It corresponds to one fishing event. And then you make another random walk, get another fishing event. And then you make as many as it takes to get a good diagram. I used to do like 10,000, and then if I wanted to publish, I would do 40,000 events. But now Matthew had, for his big calculation that I mentioned, I think he's done a million events for each fish, and to get really good small error bars on the results. It doesn't mean the results are reliable to that degree, but at least you know what the calculation says, very precisely because of that. So it's very easy to understand, I think, conceptually, because it's just like doing an experiment. So you get out 50,000 different results, and that means also 50,000 pairs of primary fragments, each one different excitation in the two every time, different amount of angular momentum in the two in principle every time, and so on. So you get an entire distribution, and you can widen that to, at the same time, as I mentioned, for each look at each scission configuration and try to extract both the kinetic energy and also the individual excitations energies. You can get TKE gated yields and so on. So, but the important thing is you get distributions.
And it looks like that was the last question for today.
Good.
Yeah, and everybody's thanking you for the presentation. So thank you very much. I think that was a really great presentation. And I think, yep.
So I stop share here. And all right, so thank you. Lunch for me.
Thank you, Jorgen. Great presentation.
Bye, Jorgen.
Time to have lunch. How do I get out of this now? Leave. I do. All right.